Hi, I'm
Hi.
Léon, and with Louis, we are going to present to you Infinity, an oral field modeling approach for Reynolds-Averaged Navier-Stokes equations. So we'll try to come up with a deep learning surrogate model to accelerate design optimization or exploration. Traditionally, surrogate models are numerical solvers that are very computationally costly, especially since the new simulation needs to be run again for new boundary conditions. So that's why for optimization, it's very prohibitive in terms of computational costs. So that's why using deep learning methods seems a pretty natural idea for surrogate modeling. However, there are different challenges that are hard to overcome for traditional deep learning methods. The first one being the scarcity of data. Since it's costly to create data, there is not a lot of it. In addition, meshes in real-world applications are huge, so it's hard to process in one shot. In addition, there are multi-scale phenomena that are quite hard to tackle. Around the airfoil, there is turbulence, high-frequency patterns can be chaotic, mixed with low-frequency ones. And also, there are different geometries that the networks need to adapt to, so different airfoil shapes, for instance. So that's why we think that implicit neural representations, or INR, are a good fit to tackle this problem. So INR is quite simple. It's just a function that will map the coordinates value to a function value. So for instance, it's useful to reconstruct a physical field. We'll just give a coordinate and we give the field at this given coordinate. In order to train it, it's the usual thing. We minimize a reconstruction loss. And at each reference time, it will just give you the output field. And it's a natural way to model continuous physical fields since it's continuous. Also, it can capture high frequency patterns, and it's robust to subsampling of the domain since it's continuous. And also, but the one problem is that it can only represent one function. And in our case, with different geometries, it cannot adapt to this. So that's why we use modulated INR. We have an hypernetwork that will modulate the weight of the INR, and then it can adapt to different geometries. So the hypernetwork will take a code ZI as input. And the training is a bit different. We need an inner loop that will adapt the code to the geometry, and then an outer loop that will adapt the common parameters. And then at inference time, we'll only adapt the code, which is very quick. And that's why it's called auto-decoding, since we can encode and decode with only the die. So now we present our method.
Thank you, Leon. So with Infinity, we wanted to propose a model for solving Ron's equations using modulated implicit neural representations. So as a recap, the task at hand is to infer the physical fields around the airfoil given the airfoil shape and some boundary condition parameters. The airfoil shape is implicitly observed through a distance functions defined over the domain, and also given a normal function that is defined over the surface of the shape. The boundary condition is the inlet velocity, which represents the far field limit value of the velocity in the field, in the domain. The method that we propose adopts the encode process decode procedure, where each encoding and decoding steps occur with an implicit neural representation, and the physical fields that we decode are the velocities, horizontal and vertical, and the pressure and the turbulent viscosity. We validated this model on F-France, a challenging benchmark for solving Ron's equation. We had 800 samples for training, 200 for testing, and the meshes were quite large, around 200,000 nodes. The Reynolds number corresponds to turbulent or almost turbulent flows, and the geometric parameterization of the shapes were done through an ARCA airfoil model. The results that we obtained are quite encouraging because our method is able to accurately predict the physical fields, especially the pressure at the surface, which is crucial for industrial applications. Indeed, a high accuracy on the pressure results in a strong alignment for the computed forces, which are the drag and the lift. We observed this strong alignment with Infinity's predictions, which is a good step. The mean inference time is of 100 milliseconds, which is far less than the 20 minutes that are needed to obtain a single simulation. And in addition, we can obtain the full mesh in one shot, which is a good fit. Thank you for your attention. And if you have any questions, don't hesitate to send us an email at these addresses. Thank you.
Thank you. Bye-bye.